Okay, folks, it's 10 o'clock. Let's get started. I'm sorry for the disruption in the last 2 weeks, but I did my best to accommodate that absence by preparing these videos and posting them. Now, don't put your guards down as far as this business is concerned. Right now, last 3 weeks we have been doing mechanisms, and that is going to pretty much end either by Friday or by Monday. Now, I have a couple of problems that I'm going to do today, but the reason that I want to devote the Thursday's lecture and Friday's lab uh, to this particular topic is that on the final exam, you will have a problem where you have to generate, create a mechanism, put some physics into it, etc., etc., and plot, something against something else, get a trace and things like that. But also notice that all the problems that we have done so far were very simple formulas. In other words, for example, the very first one that I did, block translating along a track, constant acceleration. That means the formula for displacement was integral of acceleration twice, which gave you t squared. So this displacement equal to t squared. Other problem, displacement equal to maybe velocity, constant velocity times t. An expression that you could put down as a formula in your program. But if your expression is not that simple, for example, between time 1 and 2, this is the velocity. Between time 2 and 3, it stops. Between time 3 and 4, velocity is such and such. Then you cannot write it as a single formula. You have to write a few lines of code. And that's standard, MATLAB type code. It's not MATLAB. It's C lines, a couple of lines of C and things like that. And we're going to do that on Thursday and Friday. Okay. So don't put your guards down, because by the end of that topic, mechanism done. The remaining part of the course, which is only 2 weeks, that's 1/6 of the course, is going to be on something that is completely different. It's not dealing with mechanism. It has to do with design table and parameterizing stuff like that. All right. Now, first of all, are there any questions? Are there any questions based on the absence of 2 weeks, pretty much? Okay. So today I'm going to do two problems for you. This is going to be the second one, actually. And I will do a universal joint for you, model something like that. We'll talk about that later on. We'll talk about this later on. But this one, there's nothing new. All the joints you should be able to do, and I have done it for you in other problems, in other type of problems. So I'm going to put it together and do this problem for you. So basically, we have a stationary base here, right there, stationary base. And on it, there is two links like that. And this is a third link. Let's think about this thing as a welding gun. So this piece is supposed to go and weld two pieces together along that seam. Okay? I don't have to worry about the parts. It's that path. Okay? So think about it in that context. Now, obviously, this can rotate. This is going to be a revolute joint. I don't know what the range of motion is, of course. It can be between, I don't know, 30 degrees and 90 degrees, whatever. So can this can also, this is a revolute joint. This thing can go up and down because that seam is at a slanted angle. On purpose, I want to make it slanted. And notice that it can go up and down because as it travels, but it can also spin unless I make it prismatic. And in the case of a welding gun, that thing cannot spin. Otherwise, you don't have a control over, the machine, basically. So we're going to have a revolute, prismatic, and a point curve joint. All of these you have done separately. Now we're going to put it together in this problem. I'm going to ignore all dimensions. But when I say ignore all dimension, is that notice that hypothetically, if this path was too long in this direction, that gun will never be able to reach the extremity. So yes, I ignore dimension, but if I wanted to go all the way around, then of course those dimensions must be meaningful. You cannot have this thing be 1 mile long and this may be 2-3 inches. Any questions here? Okay, so let's go ahead. Ignoring all dimension with that caveat. So let's start with the product file. Immediately save it. Now, I don't like to work in this environment. I want to go to assembly design, although it can be done here. Immediately I save it, file, save management, save as, desktop, new folder. This is group 2, problem 1. Okay. Let me create my base first. So insert a new part in there. And I'm going to call this thing base. There is the part name down below, and this is the instance name. And let's make it. Now, if I double click on this, you know that you're not going to go anywhere, because notice that there's 2 gears here. 2 gears. You're in assembly design already. If I double click on this thing, nothing is going to happen. You're already in assembly design. But if you expand this thing, this is part design. That's why you double click on the second line, so that it throws you into the part design. Something that you may not have noticed. But anyway, on this plane, I will sketch. And this is how I'm going to do that. The end result, however you do it, doesn't matter to me, as long as you get the thing that we want. So I'm going to do it like this. Maybe you see something either new or just refresh your memory. I'm going to multi-pad this. There's 3 curves here. This is the square out there. So let me make this thing maybe 0.1. There we are. This is going to be the middle shaft. So let me make it, I don't know, 4, 5. And this is going, actually, yeah, this is the middle shaft. The other one was the thin one in the middle. So I'll make it 5 here. Let's see if it works. No, this one should be higher. Maybe 5.5. Yeah, the other way around. Make this thing 6. Come on. Good. That's what I wanted. Okay, good. Do it any way you want. Now, this guy doesn't go anywhere. That's the base of the structure, the base of the assembly. And that path, that seam that is going to be welded is not going to go anywhere either. So I can make that seam as a separate part, insert a new part and draw that, or make it this, make it part of this. So right now I'm going to do that. I'm going to do that. That path, I'm going to put it as belonging to the base, okay? Because they're both stationary, they don't go anywhere. Okay, so how am I going to do this? I want this path to be slanted, so I need a slanted plane. Let's do this, slanted plane. And I want it, because it's slanted, I'm going to do it with angle normal to a plane. And read this thing carefully. It says, what is the rotation axis? The rotation of that plane. So there we are. What is the reference plane? And that means that this angle that you give me is with respect to what? With respect to that plane. Notice that right now it's vertical, but if I keep changing the angle here, it will turn and rotate until I'm happy. Oops. There we are. We're going to draw that path on this slanted plane. So on this plane, I will sketch anything that I want. Let's fit it in. Fit. Okay, so let me draw something like that. You can draw an ellipse, you can draw a circle or a profile. It really doesn't matter. I'm making a spline, something like this. I think that did it. Exit. There we are. This is at an angle. You can see that. It's not horizontal. If it was horizontal, this link 3 would not go up and down, which is fine. There's nothing wrong with it. It can be horizontal. That's pretty much it. So this is more structure. Let's say, oh, you know what? Why don't I, on purpose, I'm going to make a point here also while I'm while I made this path, exit, in that part, I'll make a point on that path. And you'll see why. It doesn't matter what point, I just made a point there. You'll see why I need this point. You don't really need it, but that's fine. Save everything. All right, let's insert our link 1. Link 1 is, I'll call this thing link 1. And this is link 2 and link 3. So insert a new part, say no, change the name to link 1, properties, there's the name, link 1, and this is the other one, link 1. Let's make it. All right, so for me, it's very convenient to use this as the sketch plane, this thing, because I want to project that little circle on it, project that circle on it. There we are, you see that? And do the rest of the link. It really doesn't matter, so I'll just make something up. It's a fat link 1. There. Exit. And by the way, I want to hold right there, so let's go back there and make a hole. Exit. And pad. Okay, that's too high. 0.3. Okay, good. So that's link 1. I also need link 2. Okay, a couple of comments before I go there. First of all, let's save everything. And I hope on the final exam, a problem like that is given to you, everybody makes it, everybody gets things correctly. But what if it doesn't? What if it doesn't work at the end? You spent all this time, eventually you cannot make this thing move. Well, first of all, there's going to be substantial deduction of mark, whatever it is. We already saw some of the stuff that I posted on the last assignment, whatever. But at least I want to give you some part marks. Well, first of all, I'm going to move everything apart later on and update. They better go back to where they belong, okay? But at least make things the way I want it. Don't go and make things the way you want it, and it doesn't work anyways, okay? So if I want 2 holes, make 2 holes. Although for the purpose of mechanism, it makes no difference. These can be 2 pins sticking out. The same mechanism works with 2 holes or 2 pins. Basically, you need access later on. Anyway, that was my comment. So insert new part, link 2. Say no. Properties, link 2, and link 2. And let's go make it. Double click. Okay, very good. This is convenient for me. I will sketch on it. Why don't I project that circle? There we are. And do the rest of it. So normal view is right here. And the rest of it looks something like this. Maybe something like that. Okay. And then a little circle there. That link 3 is going to go in it. Exit. Now, I want this guy to be a protrusion, embossment, protrusion, pin, whatever, and this one to be a hole. Okay, so why don't I do a multi-path? If you did it as 2 holes, I have no problem. Make it work. It's the same mechanism. But I wanted to do it like this. Oops. Really? What do you think? I get a message like this. Well, first of all, if you don't know, go delete that sketch and do it over. My suspicion is that this is not a closed path. So let's go back in it. Remember that last piece? Let's get rid of this. Let's go there. Let's go back to that path. And there is something called sketch analysis, sketch tools, sketch analysis, open. Okay, so let's delete this, or close it, okay, or delete it. Do it again. I don't care. Just make that part. So exit. I think it's going to pad this time because not that. Cancel. Oh yeah. Wait. I set the pin. Okay, good. So there we are. So this is, we make it point, I don't know, 0.2. This one is the, wait a minute, what's this? Cancel. Okay, so that is 0.3. I'll give it 0.3. This is one of these holes. I don't know which one though. I don't know. I'll make this thing 0, and the other one, yeah, right there. That I make it 0.5. Look, I don't care how you do it. Make something like this. Good. Save everything. Go all the way to the top. Save everything. Okay, now let's insert the third link. Insert new part. No. Right click properties. Link 3 and link 3. Okay, good. Make it. Double click on this. On that plane, I will sketch. Project that circle. There we are. Exit and pad it in both directions. And on purpose, I'm going to make a point here at the bottom of the circle, and then eventually I'm going to put in that curve, okay? Now, if you're following the book, or if you have the book, whatever, the tip is actually pointy, okay? If it's a pointy, there's a couple more steps that you have to go through in order to put the tip of that on that curve. But if I make a point, no issue. So I'll make a point here, and the method of making a point is on the center of a circle, and there's my circle. It already created something there, and we are good. All right, so save everything. This stuff that we did has nothing to do with this course. It has to do with what Dr. Pushko taught you. Okay. So now we're going to put the assembly constraints and eventually use the magic wand to create the joints. So first thing I'm going to do is I'm going to anchor something. I'm going to anchor the base. Okay. So anchor the base, which automatically the curve is going to be anchored with it because it belongs to it. And we're going to move these things apart so that makes the process easier to see, like that, and like this, and like this. Okay, let me put this thing in there. So coincidence between this axis and that axis, and coincidence between this plane and that plane. And if it doesn't look good, we're going to flip the axis. It doesn't look good. So we go here. Although as a mechanism, it makes no difference doing it the way I did it right now, and what I'm going to do then is going to work the same way. As a mechanism, it makes no difference. And now coincidence between this axis and that axis, and coincidence between this plane and this plane. Again, if it doesn't look good, yeah, it doesn't look good. Basically, these arrows means that these two faces should point to each other, okay, not in the same direction. Okay, very good. Okay, let's stick this thing in there. Coincidence between this axis and that axis. Now this is going to, if that's all I did, it's going to become a cylindrical joint, axis to axis. We can go up and down, it can spin. I want to take away that spinning motion, and one way of doing that is making sure that the vertical plane of the link 3 and a vertical plane of that link 2, the angle stays the same. That's one way of doing it. So I'm going to say angle constraint. This is the angle constraint. Angle. Between the YZ plane of link 2, for example, and the YZ plane of link 3, whatever that angle is, keep it the same. It happens to be 0, which is fine. Nothing changed. That's because it was already 0. I just translated them. Good. So I think we are good. Oh, this point, I'm going to bring it to that curve and make him coincident, because you know what the nature of the joint is going to be, point curve joint. But a point curve joint cannot be done unless the point is on the curve. Same thing with point surface, by the way. So to do that, I'm going to say coincidence between this point and that point that I created, and update. Okay, good. Now, this last constraint, if I left it like this, eventually it becomes some kind of a joint. Can you tell me? Good multiple choice question. I did this. What joint will that give you if you use the magic wand? What do you say? If you use the magic wand, and this constraint that I put in there, I put this point on that point, what is the joint that's guaranteed to be created? Good multiple choice question. Anyone? You should know that. Otherwise, you lost 1 mark on the multiple choice question. Spherical joint. And a spherical joint that's going to stay put. It's going to stay there. It's not going to go anywhere. The degree of freedom is going to be 0 because this is going to be already not moving anywhere. Not moving anywhere means good. This animation is stationary. Okay, so 2 options, you can either delete this or deactivate it. The problem, it's not a problem. The issue with deletion is that if you ever have to put this thing back on there again, you have to create a constraint again. If you deactivate it, you can always go and activate it, update, and deactivate it again. It's up to you. I'm going to deactivate. Good. Save everything. You're almost done with this problem. Yeah, so we go to digital markup, DMU kinematics, get the magic wand out, new mechanism, auto create. So you're going to have 2 revolute joints and one prismatic. And each one of them has 1 degree of freedom, and therefore 3 degrees of freedom altogether. Okay, first of all, I need a point curve joint. Point curve joint. The curve is obvious. The point is that, but it won't let me take it because there are 2 points sitting on top of each other. It's the point at the bottom of the link that you have to take. You can either hide this thing here, you can hide it, and obviously when you hide it, the one on the top is going to be hidden, and now I can select this, okay? Because the other guy was sitting on top of that. It won't let me do that. Or you can go to the 3. Makes no difference. And of course, degree of freedom is 1. To make it animate, you can make the revolute joint angle driven, or this one angle driven, or the prismatic joint up and down length driven. The problem is that I don't know what the range of motion is, but I know that point curve joint should go all the way around. So I'm going to make that length driven, okay? Just to make it look better. That's all. Because I can do these angle driven or this prismatic one length driven, except that the range of motion may be so that it doesn't go all the way to the top, all the way to the bottom. So I make it length driven. The total length of this apparently is 9.7 inches. So we say, okay, mechanism can be simulated, and let's check it out. Okay, good. Let's put it all the way to the 0 location. Create a simulation. The rest of the stuff is the stuff that you know how to do. I'm not going to spend too much time on it. Let me just make a cartoon for you. Insert, because I'm going to ask some questions. Smooth this thing out of the way. Bring this thing down. Anything that's bothering you, you can hide all these planes and all these things. Make it go around. in the same direction. Let's slow it down here a little bit. Okay, good. Now you can put physics on it. In other words, if you know the velocity of the welding gun as it's welding, and I think it doesn't have to be a rocket scientist to know that it probably should be a constant velocity, because you don't want to take the gun and slow down, etc. So fine, you can put the physics into it. But I have a question for you. What is the acceleration of this point? This point, which is welding along that seam, what is the acceleration of it? It's moving. That point is moving. Okay. What is the acceleration? If it's moving, maybe it has an acceleration. Yeah. What is the acceleration of it? Is that again? Zero. Okay. Yeah. It is changing in 3 dimension. Yes. Okay. You should, let me ask you this: if you are standing on a merry-go-round or sitting on a horse on a merry-go-round, Ferris wheel, no merry-go-round, okay, and it's going at a constant speed, do you have zero acceleration? If the answer is yes, why are you falling off the horse? If you're falling off the horse, it means that there's something acting on you, on your mass. There must be an acceleration. The tangential acceleration is zero, not the normal one. The normal acceleration is not zero. And in fact, you have a formula from it from high school physics. V squared over R. V squared over R. If you know the velocity of that speed of that point, and if you know the radius of curvature at that location on the curve, you have an acceleration, and it's V squared over R. Where is that acceleration biggest? Where are the chances of the place that you're going to fall off the horse? If this was a horse. Yeah. Say it again. What does curviest means? Curviest means the place where it has the smallest radius of curvature. Smallest R, V squared over R, biggest acceleration. Yes, perfect. Multiple choice question. A, B, C, D. Which one of these has the biggest acceleration, etc. Anyway, no more physics into this. I'll just leave it the way it is. Any questions? Okay, if that is the case, so close, save everything, and get rid of that. Now we go to our second problem. Where have you seen things like this? I mean, what's the why do you use these universal joints? Transmit torque, and what was the last one? At an angle. Yes, transferring motion basically from one direction to another direction. If you go by you're on church, you look at the truck from underneath the truck, you see that there's this shaft coming from the engine, and it's turning like that because the engine is horizontal. The rotation of the shaft, crankshaft in the engine is horizontal like that. But this has to be transferred all the way to the rear wheel. This motion has to be rear wheel. So you use a universal joint to transfer this motion to that. Yes, but there is a problem here. If that shaft, pretend that it's the one that the RPM of the engine is going at a constant speed, 50 RPM, 1,000 RPM, whatever it is. What is the angular velocity of that slanted shaft that's coming underneath the engine and you can see it? Let's hypothetically say 500 RPM there, 500 RPM at the engine, which doesn't necessarily mean the rotation of the shaft. But anyway, what would the slanted shaft experience as far as the angular velocity RPM? Well, first of all, you can't give me the answer. I know that you can't give me the answer. But would you expect it to be a constant? Engine is constant. This angle is non-zero. Would this turn at a constant speed? The answer is no. It will turn, but it's not a constant speed. Actually, it's a fluctuating speed. It looks like this. The engine turns at constant RPM. The horizontal axis turns at constant velocity, but not the slanted one. So how do we fix this? I mean, this is useless. If that was the case, the real beautiful will feel, you know, variable velocity, right? So the way to fix it is to add another horizontal shaft at the other end of the slanted one, and that turns constant RPM into constant RPM. Not the middle one. The middle one turns at the constant, at the non-constant speed, fluctuating speed. But the maximum speed of the maximum speed of the slanted shaft is related to the RPM of the thing. The maximum, not the actual. Actually varies with time, but the maximum, they're related, and they're related through for a formula like that. In other words, this is the input shaft, output shaft, and the relationship is multiplied by cosine of the angle, whatever it is. Maximum speed compared with the input speed. So, are these legitimate to ask? Yeah, sure, right there. You're looking at it. If I give you the angle 30 degrees, you can tell me what the maximum speed of the slanted shaft is. Maximum speed. The speed is variable, but the maximum speed is related by multiplying or dividing by cosine of that angle. But I'm not worried about that right now. Okay. So I want to solve this problem for you, and I will create a dummy part called shaft orientation. Shaft orientation, which its sole purpose is to make sure that when I make the shaft, I put them together properly. That angle should be 30 degrees. So I'm going to create this dummy part for you called shaft orientation, and I do the rest. The two shafts are identical, so I'm not going to make two of them. I'll make one and use it twice as an existing component, and then eventually we're going to make the pin. Any questions here? These are the kind of things that are covered in a machine design course. Now, if you're not covering it in this machine design course, and it sounds like the answer is no, they better show you something next year. Otherwise, you have a problem. Did you guys do it? Design for failure prevention? Don't remember. But these are, you know, fundamental components of machines, and it has to be covered somewhere. Anyway, let's move on. Not worry about it. All right. So let's start with the product file. File new. Product. Immediately save. I don't like that. I go to assembly design. So file, save management, save as, up. What do I call you? Group 2. There's group 2, problem 2. Okay. So new folder, group 2, problem 2. By the way, when we talk about universal joint, it's the one that I'm doing for you. When we talk about constant velocity joint, horizontal, angle, horizontal, that's the kind of thing that you have in the truck. Then you can, it's made of two universal joints, but there is a joint called constant velocity joint that can be used for that. Okay, but I'm not doing that. I'm just using simple universal joint. So insert new part in there. Right click properties, and I will call it shaft orientation. And shaft orientation. Hopefully the spelling is right here. Orientation. It's not going to complain. It's just that it looks awkward. All right, let's make it. Ignore all dimensions. On that vertical plane, I will sketch something like that, a profile. a broken line. Oh, what is that? Okay, good. Exit. This is it. This is the shaft orientation. That angle is important, but I'm not going to worry about it. So I'm going to insert my first part, the shaft. So we go all the way up there. Save everything. Insert, insert, new part. No. Double click on, right click properties, shaft, and shaft. Okay, let's make it. The way I'm going to do it is this particular way. You can make it any way you want. I sketch on that plane something that looks like that grip. So I'm going to clean it up in just a minute. Okay, I'm going to make this nice and symmetric. This line, control that line, control the middle axis, make it symmetric. Okay, this line, control that line, control middle axis, make it symmetric. Very good. Exit, add it. Probably do make mirror extent. And I'll make this thing point, I don't know, 0.5 maybe. Okay, good, good. So on that top face, we'll sketch. I want to make room for those crosspins where it's going to go. Let's see now what have we got here. Okay, let's draw a circle here. Normal view. Oops. Okay, this point, control that line, make it coincident. Okay, good. Exit. And then I would have liked it to be a little bit to the left of it. So where is it? Oh yeah. Okay. As a mechanism, these things don't make any difference. And then I'm going to make a pocket all the way to the end, up to plane, or all the way to the end. I don't know. I'll make this plane. There we are. Okay, good. For a reason that may not be obvious to you at this point, I'm going to create a point exactly halfway between the circles on the top and the bottom. Okay? You can do it any way you want, but watch me if you haven't done it this way. So I'm going to make a point, and the method is between 2 points. The first point, I'm going to make it, create a point, and the method that I'm going to use to do that is going to be circle center, and there is my circle. There is a point. For the second point, I'm going to make it, create a point, and the method is going to be circle center, which is going to be this. Say okay. So we create a point between this point and that point, but the ratio, either you say middle point or put 0.5 here. Doesn't matter. So I'll say middle point right there. Okay, good. So those 2 points are actually temporary points that were made in order to do this last operation. Good. Now let's do the shaft, the shaft of actually this this thing. So on that face, I will sketch. I forgot to do that over the first group, so I came back and cleaned it up. This is going to be the shaft, the actual shaft. Exit. Pad it. Yeah, okay, good. Very good. So this is all done. Now I want to use this guy for the other fellow, but in order for me to do that, first I have to save this. Without saving, I cannot say use existing component. Okay, so I go there, all the way to the top, click on the floppy, There we are. And then insert existing component. If it's too much of a hassle, go make another one or copy and paste. Doesn't matter. This is not the right one. This is not you. This was the earlier class. So group desktop, group 2. Did I miss it? Group 2, problem 2 right there. And the shaft. And we say OK. Good. They're sitting on top of each other. So let me separate them so that you can see it better. So let me translate this thing in the direction X. Yeah. All right, fine. And then maybe rotate it. I'll just leave it the way it is for now. Okay. I want to make the crossbit. Okay, and here's the way I'm going to do that. First of all, insert existing component, new part in there. No. I'm going to call this thing crosspin. Right click, properties, crosspin. And crosspin. Crosspin. Okay, let's make it. Right there. Double click on it. You can make that thing any way you want, but here's how I'm going to do that. On that top face, I will sketch. I'm making the crosspin now. Why don't I project that circle? There we are. Exit. Pad it. All the way to the end. So all the way to the plane. And I'm going to select the plane. This. And there we are. But I need another one of these perpendicular to that. And if you haven't done it, here's a nice way of achieving that objective. I'm going to make a circular pattern, two of them, 90-degree apart. And what is it that I want to pattern? I want to pattern this path. And the reference is that axis. So basically it tells you when you want to pattern, you need a circular thing. What is the direction to that circular pattern? Right there. Too much of a hassle? Go make it. All right, so we go here. Oh, you know what? Oh yeah, that's right. I already made that point. I told you it's not obvious to you why I'm making that extra point because you're going to see that in a minute. So save everything. First of all, it's a good idea to separate these things, but make sure that they're more or less in the orientation that is what you really want. In other words, I don't like particularly this one. So I'm going to move and manipulate. Let me rotate that about the Z axis. Okay, I like this thing better. Maybe not. You rotate it enough. It really doesn't matter. But that's fine. I like that better. Okay, this is fine. And I'm going to move this thing, translate this thing to the Y direction, separate it like this. I'm going to move this thing over there. Just move it further back. Good. All right, first of all, we're going to anchor the orientation geometry. So anchor orientation. Did I do it? Sorry, wait a minute. No, I did. Orientation. That's done. I had already done it. I don't think I wanted to do it again. So it's already done, right there. Right? Shaft orientation. Why is that not showing up on the screen though? Oh yeah, right here. There's a green anchor there. Good, good. Okay, so I want the axis of this shaft to be aligned with the axis of the shaft orientation. So coincidence between the axis of the shaft and the axis of that orientation, and nothing is to update because I just translated in that same direction. That's why they're all already lined up. And coincidence between this point, remember I created a weird point there, this point, and I want to move it to that location. Undo. Try it again. Coincidence between this point and that point. There. and update. There. Because I want it to be positioned in the proper location. Now, coincidence between this axis and that axis, update, and coincidence between this point and that same point that I used here. If you're having a problem picking it from screen, you can always do it from the tree. You created these points. There. Let me rotate this thing a little bit because it's bothering me the way it is. So rotate about this. Cancel. Cancel. Try it again. Let's try it again. See, this is why it was not doing it the way I wanted. Rotate about this axis, but keep the constraints active, like that. Okay? Otherwise, it'll go to some weird orientation. Good. Let's put the pin in place. So coincidence between this axis, coincidence between this axis, coincidence between this axis and that axis, update, and coincidence between this axis and that axis, update. By the way, notice that I always go and update it myself. It's possible to activate something in the tools, options, etc. So automatically, as soon as you put a constraint, it's updated by the, manual without doing it manually. But all right. So first of all, is it working? Before you create the mechanism, let's save this. Because if you cannot verify it's working now without any joints, in all likelihood, you're going to run into problems later on. Not always, but in all likelihood, you will. So you do the move, manipulate, check the constraints active, rotate, for example, about this. If I move this, everything should move the way I want it. Yeah. If that doesn't work, in all likelihood, something is wrong, and you're going to have a problem. You're going to have to fix it later on. Okay. There are no joints here. It's just that the assembly constraint is respected. That's all. Good. Okay, so we're going to go to digital mockup, DMU kinematics. Okay, get the magic wand out. Where's the magic wand? New mechanism, auto create. Let's check the joints. Now, two people may be doing the same problem, but using different their own line of thought. The joints are not necessarily the same, may not be the same. Doesn't mean your mechanism is not going to work. It's just that because of the way you did it, you have different joints. It's possible. Now here we have a spherical joint, and the reason we have a spherical joint, remember I brought this shaft and put it at that location, point to point. That makes a spherical joint. I don't want that. Get rid of it. But I'm going to leave the children alone. Okay. Degree of freedom is 1. Great. So I'm going to make this shaft, which is the actual shaft, and orientation to be angle driven. So cross pin, not cross pin, shaft and orientation right there. Shaft and orientation. This one is shaft 1 and orientation, the existing component that I brought in. And this is why naming the instances is critical in these problems, because you know who's who. Okay, so this is the one that I want, shaft and orientation. Double click on it, make it angle driven, 0 to 360, and you say okay. Mechanism can be simulated. Let's do it manually first. A cartoon right there, you can see that. A cartoon. You can create a simulation and you can put the physics into it. But then you might ask yourself, wait a minute. There's nothing new. There's nothing new that you have done here. You have done cylindrical and revolute for me. So what did you teach me today? Where is that? Where is that universal joint? Okay, so let me put it this way. What was the purpose of the universal joint? Transfer this motion to that motion. What's the purpose of the pin? It does that. But am I interested in the pin? Not necessarily. I want to make this motion to go into that motion because I want to show something on the TV screen for you that things are moving, etc. That pin does nothing. If I want the stresses in the pin, that's a different story. If you want the stresses in the pin, you better know what the acceleration of the pin is. But if you just want to transfer this motion to that motion without any regard for the pin itself, why do I need the pin? Okay, that being the case, why don't I go there? Anything that's associated with the pin, I'm going to delete. So this works fine, but I've not shown you anything new. So I go here, cross pin and the shaft, delete. Don't delete the children in case you ever need it. Where's the other one? Here, shaft 1 and orientation, that's the instant, the other instant, delete. Don't delete the children. Okay. So if you look at the joints, and if you go here, you see this thing which says universal joint. Right next door, it says CV joint, constant velocity joint. Remember, shaft, horizontal, slanted, horizontal. That's not what I have. I have a universal joint, horizontal, or a direction and a direction. So this is something new. You have not done this. You click on it, and for the people in section 1 who are watching this video, I made a bad mistake. I miserably failed in finishing the problem, and I told them that watch the second video, which is this. So spin 1, direction of the spin is that axis. Spin 2, that axis, that's fine, or the axis of the shaft or the direction, it doesn't matter. And say okay. I think I'm running the same problem again. Okay, just a second. I hope I'm not going to run into the same problem again. So let's give it a try. Let's go back here. Let's go back here. You know what? I'm going to delete this universal joint. This is not my day. Try it again. Spin 1 direction, this axis. Spin 2 direction. Try it again. God. This axis, that direction. Axis of the shaft and a direction. Say okay. Really. Okay, these constraints that I deleted, I think they're sitting here. I'm going to delete this. Okay, I used the universal joint. I selected this axis and that line. Now, degree of freedom is 2, so let's see now. Angle driven. The problem is that this is going to go, yeah. Try it again. Let me go back to where I started deleting all of these things. There we are. This is where we stopped, okay? So I deleted this cross pin and shaft. I deleted this. I deleted that. Okay. Universal joint. Spin direction 1. I use this axis. Spin direction 2. I can select both of these, but okay. Do it again. right there. Spin direction 2 is right here. Too many commands. Shaft orientation, hang in there. Cylindrical revolute. We did this. Degree of freedom is 2, so I don't like that. No effect. Okay, fine. Oh my God. Okay. I have to publicly announce that I failed again. So what I'm going to do is I'm going to stop that video right here. Okay. But I will fix this. I'm going to start from here, fix it, and attach it to what I've done so far. Okay. So this video is going to be made of 2 parts. Everything up to this point, and then after I swallow my pride, do it again, attach it to the end. It'll work, believe me. So I'm doing something wrong, and I'm repeating this mistake that I made with the first group. Okay, folks, so I'm going to stop this.